Welcome. This is lecture 60, and this is the final lecture in this course on computational commutative algebra. So in this lecture we will look at some applications of Castelnuovo Mumford regularity in a problem in geometry, problem that would be stated without any reference to any. It would just be about some functions and some points. So what is the question that we want to understand? So throughout this lecture, K is algebraically closed. Okay. And we ask the following question. Let X inside Pn over K, so we can think of this as lines in Kn plus 1, okay, but take away the origin, and then we let the units act by scalar multiplication. Okay, so the points in Pn correspond to such lines. Okay, so X in Pn be a finite set. Let's say M is the cardinality of X. So we take m distinct points in Pn K, okay, and we ask when does X impose independent conditions on forms of degree d. Okay. So what does this mean? So the question, okay, what does the question mean? So if you think about the, so we consider the polynomial ring in n plus 1 variables. Okay. It is a proj of this ring. Well, the way we wrote proj here means the points that correspond to the maximal prime ideals that are not the homogeneous prime ideals that are maximal with respect to the property that they are properly inside the homogeneous maximal ideal. Okay. So a point, so that, I mean, we did, so if you have a point which is A0, so points inside here will be actually equation, in Kn plus 1 it would just be given by a whole line. So we can just write down the slope of the line like this. We actually don't care about the actual values of A0, we only care about the ratio of these numbers, okay? Because if there is a B0, B1, that would be the same point if one can be obtained from the other by multiplication by a non-zero element in K. Okay? So this is so this is the point inside Pn, that is the image of A0 An under the equivalence relation. Okay, the equivalence, so this is the equivalence class of this point. Okay. So points in Pn are not actual n plus 1 tuples, they are n plus 1 tuples with an identification. The identification is that two n plus 1 tuples are considered to be the same if one is obtained by the other by a multiplication by a non-zero element of K. Okay, so this one corresponds to the point, the maximal ideal, okay, in this thing, which is, so let's assume for simplicity that, I mean, not all of them can be 0. Okay, so let's assume for simplicity that I is the minimum, or let's call it J is the minimum I such that AI is non-zero. Okay, because we are worried about ratios, whether AI is non-zero doesn't depend on which point we take in the equivalence class. Okay. So AI is non-zero, and then we can write, so then A0, A1 up to AN This point is also the same point as 0, 0, all the way up to 0, up to this is up to j minus 1. Then we can put a 1 here by factoring out this thing, and then a j plus 1 over a j and so on. Okay. So these two are the same points. Okay. Because often we would write a point like this with a 1 somewhere. Okay. So just to clarify that they are the same points. Okay. But if you have a point like this, we can write, so the point a0, a1 up to an corresponds to the prime ideal. Okay, so we'll assume that up to aj minus 1 are zeros, so it will be x0, x1 up to xj minus 1, okay, and then xj plus 1 minus aj, xj plus 1 xj. Okay. Again, what matters is the ratio, which it is clear from this. This just says xj plus 1 is aj plus 1 over aj of xj, and that's exactly this ratio. Okay. And then so on, xn minus, sorry, not xn, an, aj xn minus an xj, so on. So this is there are n terms in n generators in this. So this is a prime ideal of height n, and is therefore a point inside Proj. Okay. So this is the identification. So, okay. So now what does the question say? A point P inside Pn imposes conditions on f. So we only have to worry about homogeneous polynomials, because if you try to evaluate f at P, then P is not a single point. P is a ratio, right? So which means if you instead of taking P, if you take some other point inside Kn plus 1 representing this, f should take the same value, and the only way that will happen is if f is homogeneous. Okay, so f is homogeneous of some degree d. Okay, so f is homogeneous. So what does so what does this mean? That is, the coefficient, so imposes conditions by vanishing, imposes conditions based on vanishing. Precisely, more precisely, okay, we can write f as some sum A indexed by some coefficient ei, where e1 plus e0 to en is d, x1, x0 to the e0 up to xn to the en. So f can be written like this. And now the condition f of p equals 0, the f of p equals 0 imposes conditions on the coefficients. Okay, so let's look at this. So each point will impose some condition, and the question therefore is, when does X impose independent conditions on forms of degree D? Okay, so let's look at what this means. Okay, so it's easy to do an example in P2. So the corresponding ring is K, X, Y, Z. Okay. If you take the point 0, 0, 1, so this is the point inside K3 corresponding to 0, 0 and a non-zero third coordinate, and all of them will correspond to the same point inside P2. Okay, so this one, okay, so f, so let's say P is this. Okay, f P is 0 if and only if the coefficient of Z to the D in F is 0. Okay. So a single point imposes a single condition in every degree. Okay. And similarly, we can do in any for other points also. It would be a little bit more complicated, and we'll see an example along the way. Okay. So so every point imposes one condition. I mean, conditions are one shouldn't say they are independent. They are related, but given a degree d, on the forms of degree d, a point will impose one condition. Okay. So for all d and for all p inside p n, it doesn't have to be true. P imposes one condition on forms of degree d. Form means homogeneous polynomial, forms of degree d. Okay. So now the question is, if you have m points, when do they impose independent conditions? Okay. So if there are m points, when will they impose m conditions? So what is, okay, so example. So example 1. Take 3 collinear points. So x is 3 collinear points. X is a set of 3 collinear points in P2. Okay. So then we may as well assume that, I mean, we can just do some change of coordinates so that it looks like this: 1, 0, 0. Okay. We can do some. Okay. This example is as general as the general case can get. 0, 1, 0 and 1, 1, 0. So now let's look at linear forms. Ax plus by plus, so we'll write the way, this is in P2, so we'll write the ring as xyz, not x1, x2, x0, x2, x1, x2. Cz equals 0. So okay, those are the variables. This one on this, so this f is this. F has to vanish here, means that a must be 0. That's from here. From here it says b must be 0, and from here it says a plus b must be 0. Okay. But these are not independent conditions. Okay. Because it only imposes 3 conditions, it only imposes 2 conditions, okay, not 3 conditions, and the linear forms form a, so this is a 3-dimensional vector space. Okay. Now we can look at a different example. Example 2. Okay. The points are not collinear, and we could take them to be like this. Again, the example is still in P2. In P2. Okay. And if you look at f, which is ax plus by plus cz, it imposes 3 conditions. It says a must be 0, b must be 0, and c must be 0. So 3 independent conditions. So here, recall that in the first example, the points were 1, 0, 0. So that corresponds to vanishing of y and z. This corresponds to vanishing of x and z, and that corresponds to the vanishing of z and x being equal to y. This is J1. Intersect the ideal of yz, xz, and x minus y, z. X minus y is to set that x is equal to y. So this is the ideal of the first point, this is the ideal of the second point, this is the ideal of the third point, 1, 1, 0. Okay, so we intersect that and then we get Z and this one. Okay, so the ideal is this. In the next example, the ideals are, this is y, z, this is defined by y comma z, this is defined by x comma z, and this is defined by x comma y. Okay, so those are these three, x comma z, x comma y, and y comma z, not in that same order, but these three. And we ask Macaulay to intersect, and that would give the ideal of, in the first example, the ideal of that set of points is this. Second example, the ideal of set of points is this. Okay? So the ideals do look slightly different. Collinear means that there is a linear form in that ideal. Okay? So it's a linear form and a quadric and a cubic, and here there are three quadrics. Okay? So we ask for the resolution of J1 and resolution of, R mod J1 and R mod J2, so that we will look proposition. M points, so x which is M points, impose independent conditions on forms of degree D if and only if rank, the Hilbert function of R mod I in degree D is n. Okay. So why is this? Because at each point it has to vanish. So to belong to, what is I? I is where I is the ideal of x. In other words, it's the intersection of the prime ideals corresponding to I goes from 1 through m, where Pi is the homogeneous prime ideal corresponding to point I in x. So x contains m points, so there are m prime ideals, intersect them, so that is the ideal I, and then rank of this Hilbert function is what we want here. So that is because the question is what sort of f will belong to I. So that's what impose conditions, independent conditions mean. So it is the checking of this Hilbert function that is required. This problem now has been translated to a problem about Hilbert function. Okay. And just another observation which we rehash in various things. Hilbert polynomial of R mod I is m, which is the number of points in x, times P0. P0 is the Hilbert polynomial of a single point. Okay, that polynomial, the constant polynomial, x choose 0. Okay, so Hilbert polynomial is this. Okay, so therefore, putting these two together from the previous lecture, the conclusion is that if D is corollary, D is greater than the regularity of R mod I, okay, then x imposes, I is the ideal of x, x imposes independent conditions on forms of degree D. Okay. In order to vanish there, it would impose conditions, and the complement will also have the same. Okay. This is an application to a problem which was a priori not stated in any of these cases. Let's look at this, the example. So we computed these two ideals, the ideals of x. There's an x1 and an x2. x1 is these 3 points and x2 is these 3 points. So in x1, that's the ideal. Okay. In x2, this is the ideal. So their generating sets look different. So we ask for its resolution. this is for J1. It has this is just the R. Okay, so it has a linear form and a cubic. Okay, and a second, this is 1. In the other case, it has 3 quadratics and 1 linear syzygy among them. So the regularities are different. Regularity for the 3 collinear points is 2. Not the collinear points. Regularity of R mod I, where I is the ideal of 3 collinear points, is 2. Well, regularity of R mod I, where I is the ideal of the 3 non-collinear points, is 1. Okay, so the regularities are different. So from the proposition, so we'll come back to this in a minute. From the proposition, we know that the Hilbert function has to agree. So the Hilbert polynomial is 3, the constant 3. Okay, so Hilbert function has to become 3 after regularity. So let's look at these 2 cases. Okay, so this is degree 0. So I'm just applying for the integers I from 0 through 9, both included, Hilbert function of R mod J1 in degree I. Okay, so if I is 0, it's just a field, both cases it is 1. If I is 1, then J1 contains a linear form, so the quotient has only dimension 2. Here, J2 doesn't contain linear form, so the quotient has dimension 3. And then for all higher things, it is 3. Okay? So in both cases, we notice that even before we attain the regularity, the Hilbert function has attained the Hilbert polynomial. Because here it's regularity, here this is degree 1, but the proposition we proved said if degree is greater than regularity, but regularity is also 1. Similarly here, the regularity is 2, but already at degree 2 itself, Hilbert function has agreed with Hilbert polynomial. So this can happen. The proposition only said that if you go past the regularity, the function agrees with the polynomial. So that we see from here. Okay. So why is it that this is agreed a little earlier? In these 2 examples, you can work it out, and I will spell it out how to do it in an exercise. Okay. So that estimate which said d greater than regularity is slightly loose in these examples, and we'll see why it is loose. Okay. So this is the end of the course. So I hope that you have learned some aspects of computational commutative algebra, and also be able to use Macaulay 2. And hopefully you can use, this will help you to use some other programs which also have its own, like Singular and Cocoa, which also have, and perhaps others also, which also have their own advantages. And so we, as I mentioned at the beginning, many of the theorems that we proved, we didn't prove it in the most general form, or for some theorems we chose we purposely chose a roundabout route so that we become familiar with computational ideas behind computations, Grosvenor bases, or being able to use Macaulay to sort of explore. Okay. So thank you for listening to me in this course.